Thank you everyone for attending the webinar. And today I'll be presenting the horn antenna far-field simulation using Ansys HFSS. So a little bit about myself, my background. So I'm an application engineer at DFE-Tech over 3 years of experience, and I'm an ANSYS certified professional in low frequency and high frequency electronics. You can see all the certificate here for the electronics low frequency, high frequency, and sales. And I'm also an HRD Corp TTT certified trainer. And if you want me to give training to your organization or universities, you can contact me after the webinar. And so what we're going to learn today, so upon completion of this webinar, we'll be able to learn to define near field and far field radiation, simulates far-field radiation of an horn antenna using HFSS. And finally, we plot the result of the far-field radiation pattern using HFSS. Next, before we go to the demonstration, we need to know the software that we use, which is the Ansys HFSS. So what is HFSS? So HFSS is a high-frequency structure simulator, and it's a general-purpose full-wave 2D and 3D electromagnetic design and simulation tool for high-frequency application. This high-frequency application, such as antenna, microchip, filter, integrated circuit IC, or printed circuit board, PCB, radio frequency component, and microwave component. And for our first agenda here, we want to know what is the radiation field. What is radiation field? So when a signal is transmitted from an antenna, you can see here is the antenna. It radiates out electromagnetic wave into free space. Then the radiation field are divided into near field and far field here. So for the near field, they are non-radiative and radiative, and then the far field. So for each of the field, reactive field is in this region, the electric and magnetic field are 90 degrees out of phase with each other, and therefore reactive. And the magnetic and electric field needs to be orthogonal with each other to radiate. So, and then the radiative field, the radiative near field is in this region, the electromagnetic field start to transition from reactive field to radiating field. Since they have not completed the transition, the shape of the radiation pattern still varies with distance. And finally, the outermost, the far field one, in this region, the electromagnetic are dominated by radiating field, where the electric field and the magnetic field are orthogonal to each other and to the direction propagation as with the plane waves. So we already know what is the near field and what is the far field. Now, I want to share about the horn antenna that we are going to simulate. So this is one of the story of the Hondel horn antenna, where this antenna gets an I'll show this video, the story about how they get a Nobel Prize using this antenna. Enjoy the video.
The place, a hilltop in New Jersey. The setting, giant antennas like monstrous eyes and ears, straining, watching, waiting.
In 19 1960, the ECHO satellite project was going to get started. The ECHO satellite project was just a giant mylar balloon in orbit.
That balloon will soon be hurtling across the sky 1,000 miles high over North America.
Bell Labs built these antennas here on Crawford Hill to send radio waves up into space, bounce them off a satellite, and then receive them on the ground and turn them back into useful telephone signals. Bob Wilson and Arno Penzias, who worked here at Bell Labs, were wondering, well, if we just point an antenna up into the sky, how much radio noise is there?
I come from a big city. I come from New York, where people don't mince words very much. Bob, on the other hand, is a Texan. I guess anybody who's seen a John Wayne movie knows what that means.
So do you want to tell us about the discovery?
Well, Arno and I set out to make the best measuring system we could to go with this antenna. We got it all together and fired it up and found more noise coming out of the antenna than we expected.
There's this uniform noise that seems to be coming from everywhere. They say, okay, well, we better check this. They discovered pigeons. These pigeons left a sticky deposit, and they were concerned that that might lead to radio noise.
We actually got a have-a-heart trap and put it right here and caught the pigeons and shipped them to a pigeon fancier. The guy took a look at them and said, these are junk pigeons, and let them go. So it wasn't long before the pigeons were back. So in the end, our technician brought in his shotgun. And in the interest of science, the pigeons were dispatched. We cleaned the pigeon poop out of the horn. Didn't make much difference. This was a big disappointment, of course. There's something wrong with this antenna. We did a few other measurements, and we're really scratching our head. We believed in physics. What's coming out has to be coming from somewhere. And then a fellow named Bernie Burke said, well, call up Bob Dickey at Princeton. Bob Dickey was a very good physicist. He was thinking about an oscillating universe, where you have a big bang and then a big crunch. And he realized that all the entropy generated during the expansion would show up as heat.
He immediately understood that this antenna here had detected the radiation left over from the universe was very hot and dense, you know, the Big Bang.
Dickey put down the phone, said, boys, we've been scooped.
Their discovery confirmed the Big Bang theory of the explosive origins of the universe.
This is where the noise from the sky and the rest of the universe, when it was just getting started, was first heard and recognized on Earth.
So here, very interesting story how they got the Nobel Prize in physics for the discovery of cosmic background using this Holmdel horn antenna. So today I'll be doing a simulation how to see the far field radiation using using Ansys HFSS. So next is the demonstration on how we use HFSS to simulate the horn antenna far field. And firstly, for the antenna design, we import the horn antenna from an existing file, and we assign the phi boundary condition to the region outside the antenna. Next, we'll set up the simulation at a frequency of 10 gigahertz here. And we create two far-field radiation sphere as shown in this two setup here. One from minus 180 to 180. So for this for this setup, we want to see the polar plot of the 3D polar plot of the radiation. And for this setup, I want to show the cut field at 0 degree phi and 90 degree phi. And for the result, we can see here for this first picture is the polar plot of the antenna gain in 3D. And for this one, the 2D plot for the far field radiation at 0 degree cut field, and this one for 90 degree cut field. For without any further ado, I will start the demonstration. So firstly, we are using this Ansys electronic desktop 2024 R1 for this mission. So for this one, I'm using the HFSS here, you can see. And for common practices, and I'm already import the design, which is the horn antenna. So for common practices, we want to copy this so that we didn't change the design file. So to copy, we simply just drag this design to this project one, and we'll create a new copy here, a new design, and we want to rename it to demo. So for this one, I'll use this demo design tool to create the simulation. And before that, I already have a practice model, which is a pre-simulated one that I've practiced before I showing the demonstration. So now we already have this antenna, the horn antenna. So we want to see the model, the solid, and the sheets. So we can see here for the horn shell, it is a perfect conductor. The uh, the thing we are using a perfect conductor for this horn shell, and inside the shell is the horn air, which is a vacuum. So inside this shell is a vacuum, and also for the uh, region, the region also vacuum. So the region is outside the antenna. Next, we want to firstly I want to rotate 90 degrees. So to rotate, we simply select this all, and we click on rotate. I want it to rotate 90 degree at the y-axis, and click OK. And click on orient to see the picture, the design perfectly here. Next, I want to assign the region, the boundaries to the region. So to do that, we simply click on this region and right click at this boundaries, assign Phoebe, and we simply click OK. Now under these boundaries, you can see the Phoebe has been assigned in the region. And next, I want to add the analysis setup at 10 gigahertz. So to do that, we simply right click on this analysis, add solution setup and advanced. So under this frequency, we simply change this to 10 gigahertz. And we click on this save field here to see the field radiation pattern after the simulation. So we simply click OK and OK. So everything is default under 10 gigahertz. Okay, now you can see the simulation, the setup already been set. Next, for the radiation sphere, I want to create a radiation far field radiation sphere. So we simply insert under this radiation, right click, insert far field radiation setup, and we click on infinite sphere here. So we start at -8 180 degree, stop at 180 degree, and to step size. And the theta is start 0 and stop at 180 with a step size of 2. And then for the coordinate system, we want to use the theta file. And then we simply click OK. So under this radiation, we can see the infinite sphere here. And I want to set another one, another infinite sphere. So we insert the far field again. And this time I want it to be start from 0. For the file, I want to start at 0 to 90 with 90 step size. And theta is from -180 to 180 with 2 step size. And this and then we just click OK. And now we can see here there are 2 infinite sphere. So let me rename this to, we want to see this one is 5 cuts, where we want to see the radiation field cut at 0 degree and cut at 90 degree. Next, we want to analyze this. So before we analyze, we go to the simulation here. So it's a very good practice that we validate this first. And if we click this and everything checks with the green check mark here, then this means that this simulation is good to simulate. And to simulate it, we simply go to this analysis at the setup one here, and we right click and just click analyze. So for my previous pre-simulated model, it takes around 15 minutes to simulate. So I'm not going to simulate this here because it will take times to simulate, and I don't want to waste our time here. And so we just simply go to our pre-simulated simulation here. So after we simulate, so this is the practice model that I've done before. So we can see the result for the first one. We want to see the gain, the total gain in dB for the first infinite sphere, which is called the gain of the far field radiation. And next we have this. Let me click on Orient first. Okay. Next we have the first gain plot here. This is the gain at using the 5 cuts radiation sphere, infinite sphere, where we want to see the pattern cut at 0 degree. And for the third plot is want to see the gain cut at 90 degree. So what is the cut at 0 degree and 90 degree? You can see here, this is the 3D result. If we cut at 0 degree here, you can see here 0 degree, right, 5. So if we cut this, you can see this is the in 2D, the shape. It's like this, right? So let's see. You can see if it is 0 degree, after cut, you can see it's about the same as the 3D. And if we cut at 90 degree, so the shape will be like this. For the 2D, will be shaped like this. So we can see from plot 3 here. So you can see the 2D plot of the gain cut at 90 degree. So the shape is about the same. And you can also see the plot. You can show it in the modular window so that you can see how it really is radiating at this model, at this horn antenna. You can see uh, how the radiation, the fluffy radiation really radiate here at the horn antenna. So you can see it in 3D, and you can also observe it in 2D, where we cut it at 90 degree and 0 degree. So that's it. This is the demonstration on how we uh, simulate the fluffy radiation of the horn antenna. So I'll go back to the slides. So today is a very simple demonstration on how we do the horn fluffy radiation on the horn antenna. So now is the time that for question and answer. If you have any question, you can ask me or put it at the chat box. And yeah, I'll be waiting for your question. And meanwhile, I think Zuleika, you have while waiting for the question, I think Zuleika has something to share with us.
Thank you, Mr. Farhans. While we are waiting the question, I have launched a poll. Please select the appropriate response and click submit. We love to hear your feedback.
So if we don't have more question, I just proceed to the conclusion. So for the summary of the learning objective, we already defined what is the near field and the far field radiation. We already simulates the far field radiation of a horn antenna using Ansys HFSS, and we already plot the far field radiation pattern and the post processing of using HFSS. So I think for all the learning objective, we already checked all. So now I want to thank you for attending this very short webinar on how to uh, simulate the fluffy radiation of a horn antenna. Next, I will pass the screen to Zuleika for the instruction.
All right. Before we go, don't forget to scan the QR code and follow us on your favorite social media. As you can see on the screens, you can follow us on Facebook, LinkedIn, Twitter, YouTube, and Instagram. All the information will be loaded here. Big thank you to everyone for being here today. We really appreciate you taking the time to join us. I hope the insights we share were useful and give you a better understanding of the topic. If you have any question or need more resources, feel free to reach out. We'll be uploading the session recording to our YouTube channel soon. Thanks again for joining us, and we can't wait to see you in the future session. Have a wonderful day.